Yeah, hi. Hello, everyone. So we are really excited and happy to share this new tool with you about visualization tools in this tech talk. And to get started and basically get you all warmed up, we have prepared a few questions. So first one is, what is your favorite plotting library? So there should be a poll coming up from Zoom. So we have the choices Plotly, Matplotlib, Excel, or maybe something else.
Okay, so we have close to half going with Matplotlib, and then Plotly and Excel basically tied, although technically Plotly comes in third. And then we have just shortly after that something else. So pretty even split on ranks 2 to 4. Matthias, what's your take on this?
Yeah, that's very good actually, because I guess many then of you will learn something new today, or will maybe convinced to try some other plotting library in the future. We'll see.
Okay.
Okay, let's go over to question number 2. How often do you read log files? Recreationally? Fairly often? Every once in a while? Oh, what's a log file?
So let's see. Let's see how many recreational users we have finished. Okay, so we have fairly often and every once in a while as the dominating factors. And then only 10% of people read the Gurobi log files recreationally. Ed, would you count yourself as somebody who reads log files recreationally?
No, I only when I'm recreating, excuse me, I don't find myself reading log files, but I read them an awful lot when working.
Okay, that's fair enough.
Yep.
Matthias, would you
Cool.
consider yourself a recreational log
Yeah, I
file
guess
user?
so.
Yeah.
But in the humorous way, as it's meant in this question. So
All right.
okay, cool. So we have one last question, and this is maybe a bit more involved, so we need to explain a few details here. So question is, which parameter setting would you select based on the results we're seeing here? So this is a plot showing 5 different runs of Gurobi, each with 3 different random seeds. And on the y-axis, you see the runtime in logarithmic scale. And on the x-axis and also in the colors, you see the different settings that we used. So you have now a choice of 5 different answers.
And do remember the runtime on the y-axis is logarithmic. So that's something to look out for. And yes, when it says 912, this means default settings. So, Ed, I'm going to start with you. What would be your pick in this question?
So I would lean towards 912 cuts 0. It's got the best result except for the cut 0 heuristic 0.1, but it is much less variable. It I think dominates default 912 and 912 heuristic 0.1. So really it boils down to 3, the first, second, and fourth. And I'm going to pick the second one. It's got a bit more variability, but I'm willing to tolerate that. The first one is too variable. The fourth one is nicely bunched together, but with a relatively slow average time. So that's my take.
All right, Matthias, what's your
I think I would just push my luck and go with the first setting. So cut 0 and heuristic 0.1.
really?
And then just run this on multiple seeds every time and hope for the best.
Okay. Well, it depends on the model, right? I mean, if you have
Yeah.
enough, or on your machine, if you have enough cores, then sure. I would
Basically
actually
exploiting performance variability to the fullest here.
Yeah, although we do always recommend our customers not to tune on seeds. Well, this is not tuning on seeds, but it's kind of, yeah, I don't know. I think I would go the exact opposite route if I was to look at this, and I would go with cuts equal to. And the reason is that because I'm really afraid of this log scale. So the first one arrives at 500 seconds or close to that, which is a lot. For a model that, in cuts equal to has a runtime 20, 30 seconds, and it's predictable and you're there. So yeah, we know it's only 3 seeds. And that would actually probably be the next step here, is to run this for more seeds and see how it's going. Okay, but I think we also have Zachary now raising his hand. So Zachary.
Hey, how's it going? So I would go with the cut to, because a lot of times I'm mixing a Gurobi optimization with a pre-data process and a post-data process. And if I know that the time is like cropped like that tightly, it helps me tune everything else before and after. So that's how I would look at that. How do I go?
Thanks, Zachary.
Yep. Cool.
All right.
Yeah, thank you. Thank you for your input. Okay, now let's get over to actually inspect a log file in detail first before we go to the more fancy stuff. And for this, we have prepared one. And Richard, would you do us the favor and guide us through this log file?
Sure.
Basically tell us what we see here.
Sure. So this is going to be a very high level just overview of giving you an idea of that. When we say log file, when it comes to Gurobi log, it's a bit more than just saying, timestamp and here something happened. It really gives you a lot of insight information into what the algorithms actually did, and a lot of things that give you information of how to deal with the model that you just solved. So just in the beginning, you can already see what Gurobi version you're running, which parameter you've set, and just based on this, it's already a lot of information of whether you're running defaults. Are you having a specific MIP gap setting? In this case, we're at 5%, for example. And then after this, we start with the model statistics, and you can think of these as like a screenshot of your model. So how many rows, columns, also of your machine, how many threads do you have available? What's the model fingerprint? So that's basically a hash of all the model attributes, which kind of make, if you solve 2 models, one after the other, and they have the same fingerprint, it means that they are almost certainly the same model, or said differently, if the fingerprint is differently, they're certainly not the same. And then we have some coefficient statistics, and this already gives us some very important information, such as in this case, we have a warning that says this contains large bounds, and please consider reformulating. So already some information in the log right there that can help you work with your model. And then it really goes into the algorithmic part in the next section, where we start with pre-solve. Now, pre-solve is the part where we basically massage the problem to make it more palatable for Gurobi. So do substitutions, reduce size, change the numerics such that it is better for the remaining algorithms to run. And so this is some interesting information that we have about that here. And from there, we go to the LP relaxation. So if it's a MIP, it's an LP relaxation. Otherwise, it would just be the LP algorithm that runs. And so it tells you what happened. It tells you how many iterations, like how simplex is doing in this case, what solved the model. In this case, it was dual simplex. And of course, what root relaxation value you got. So what objective function value you got. And then after this, we come to the part that I would say is the majority of our log files, is the biggest part. And this is the node log. And so basically, when you have the branch and bound approach that, every modern solver uses, then you start from a root node, and then from there, you kind of successively explore a tree where you're trying to find new solutions or cut off other parts. And so this is the representation of that in text form is kind of represented here. And so on the left-hand side, you have the nodes, the number of explored and unexplored nodes. So this is all related to tree size, as well as also in the in the current node that you're currently exploring, the objective function value, the depth, and the number of integer infeasibilities. So it gives you like a snapshot of the node I just solved. Where are we? What's the objective function value and how deep you are in the tree? The next section, next three columns is really the one that most people look at, which is the incumbent. So what's the best solution you've currently found? Your best bound, so the lower bound that comes to you that you're trying to match such that you minimize or you have a minimal gap, which is the next column there. And then we have the final two. Second to last is the iterations per node. This is often overlooked, but this is really cool because it basically tells you how much effort do you put into solving a single node. And it can tell you a lot about how your node LPs differ from node to node, et cetera, et cetera. And then finally, of course, time, which is self-explanatory. And so as you go down this node log, you can see in the beginning, you have a lot of stuff in the root node. We have 0 zeros on the left. That means root node. And then we get out of the root node and then we start with a branching. We see how the gap with a percentage of 12% and so on. So we go down. So you can really see it's a story that is being told here in the log, how you're finding your way through the tree. And then finally, if we scroll all the way down, we found a solution that is below the 5% we specified in MIPGAP. And we have a summary here. We say how many cutting planes we had, which ones, and finally, of course, the optimal solution found and the gap and the time it took. So it's really a story that is being told. But on the other hand, and this is kind of the point of the talk, it's a story that's told in text form, let's say, or in cryptic, like numbers and symbols. And so the question now is, can we do something that is better than that? Thank you, Matthias.
Exactly. This is exactly the point of this talk. And so we saw this can be difficult to read and interpret, but it is the standard way, basically, to document solver progress and also the final results. And this is what we want to change. So not the standard way, but that it's so difficult to read those log files. Now, this is where GRB Log Tools comes into play. So what is this? This is an open source Python package written and developed by our Gurobi support team that can read the log files for you and then make them available as pandas data frames or also an Excel spreadsheet. And when using Python, there are also some routines included for interactive plotting, for instance, in Jupyter Notebooks, or preferably in Jupyter Notebooks. And basically all you have to do is to run pip install GRB Log Tools and you're good to go. So this is especially helpful if you're not like a cipher down here in the matrix and who can basically read all this matrix code just like this. Okay, now let's look at an example. So we are here in a Jupyter Notebook, and if I prefix the cell with an exclamation mark, I can run a command line run or execution. So let's just solve an instance with Gurobi. Here I chose MISC07 and I saved the log file into gurobi.log. And now here we see the log file. This is very similar to the one that Richard just guided us through. And now all we have to do is we import GRB Log Tools and call getDataFrame and pass this gurobi.log as a parameter. Now we get a data frame, this summary data frame, and this is how it looks like. So here we see the version of Gurobi that was used. We see the model name, we see the node count, right? So these are just the numbers that we just parsed from this log file. But now they are in a, I'd say, more manageable form, in a tabular form, and are more easily handleable. So you don't have to, I don't know, go through this log file. But of course, the real that the proper use case for GRB Log Tools is not to parse a single log file, because a single log file is still fairly easy to go through by hand or manually. But now we just want to look at what would happen if we pass the wildcard symbol and just grab the data from just a bunch of log files. So here we see there are 63 rows and 60 columns. So for every log file that we parsed, we get a new row, and every row contains those columns or pieces of information that we got from the single log files. Here now there are a few more columns than in the data frame before, because we also grabbed the parameters that we changed in the different runs. So here you can see the pre-solve parameter, for instance, was changed in those runs to be 1 or 2, but it wasn't changed in those other runs. So there's no proper number here. All right. And now with this at our Pythonic fingertips, we can do all kinds of analysis and visualization tools that we can just throw at this database or throw at this data frame. And GRB Log Tools comes with a convenient plot function that looks like this. So you just run plot on the summary data frame that we just generated, and then you are presented with a selector widget where you can select what you actually want to plot for your X and Y and color. And let's just go with a bar chart first. And as soon as you select the type, the chart will be generated with the selectors that you did before. So you now see on the x-axis the different logs that we have. On the y-axis, you see the runtime, and the color is separated, or the color is used to visualize the different seeds that we used. And you can also update this to use a logarithmic axis. And the nice thing here is that this is all interactive. So you can basically just choose whatever you want to in those selectors and explore the data frame that you generated before, that you parsed from your log files. So all available columns in this data frame can actually be selected for plotting. But if you don't select them, as you saw up here, a sensible default will be chosen. So for instance, is having the log on the X and the runtime on the Y-axis.
We have a question in the chat about the Y options again. I'd like to show the Y options. Let's actually show something like this. Can you, for example, put the number of processed nodes, so the node count exactly? Mm-hmm. Okay. So here, so this is actually interesting. So you can actually see in the different, with the different settings, how the number of nodes processed differed quite a bit. Exactly. So this was but we didn't even see cuts to heuristics equal 0.1 as an option. So it wasn't actually performing that well from a runtime perspective, yet it had a lower node count. Ed, what would you make of this?
I would want to see how this relates to runtime. I mean, my view is node count is probably pretty closely correlated to runtime. It would be interesting to actually create another statistic, ratio of node count to runtime, and then look for any sort of outlier where, you had a run that took a long time, but didn't do very many nodes. That might be interesting to look at. There might be an opportunity, for some performance improvements on that run. Something unusual is happening there, like, heuristics are going wild and spending an awful lot of time. And if that time is not needed, maybe there's something you can do there. But I'm going to bet that if you go back to the old plot and compare it where we looked at runtime instead of node count, that it looks pretty similar.
And by the way, if you recognize this picture, so this is what we used for this poll question for the third one, just with a selection of just a few of those logs. But this is how easy you can get those box plots of performance runs. So I said you have those interactive parameters, but to basically as a shorthand, you can also set any of those selectors beforehand and basically predetermine those selector fields here and get an output right away. So here we just pre-selected the type of the chart to be a box plot, the color to go for the log, activate the logarithmic y-axis, and also passed in a title for this plot. And this now looks very similar to the plot that we saw before, right? With the poll question. The cool thing about here is that this is all interactive HTML. So you can just scroll around or zoom in or do whatever you'd like to basically explore this data in an easy and straightforward way. So this is really just one line of Python code that just generates this interactive chart. Okay, so one more thing, if this wasn't cool enough, timelines. So GRB Log Tools parses the entire log file, and what we just looked at was only the summary of the runs. But if you set the timelines equals true parameter in the get data frame function, you get two additional data frames. So you have the summary just as before, but now you also get the timelines data frame and the root LP data frame. So let's have a look at those. So this is how the timelines data frame looks like. You can already see that this is a huge data frame. So this has almost 3,500 rows, but only 17 columns. And the columns are also very different from the summary data frame that we saw before. And hopefully you still remember those column names. So these are exactly those sections that Richard showed in this colored log output. These are the different, this is basically your progress chart. And every single line in the log is represented as one new row in this data frame. And since you want to have a single data frame for all those log files, for all your log files that you parsed in, you also need to put in some basically identifiers for every row to see which run this was. So here we have this log identifier, and you also have the name of the log file and the seed and the model, the version. And for the second one, we have the root LP data frame. And as you can see here, this is an empty data frame. So why is this the case? Well, the root LP is empty because the root solving process was so quick that there wasn't a single line of progress information printed in any of those logs. So maybe you have recognized the instance. Shall we do a poll? Who recognized the instance in the chat? I don't know.
Yeah, let's see.
Yeah.
Nobody. Interesting.
But anyway, what you can see here is there is just no root LP progress because we just solved this in 0.0 seconds, so in a fraction of a second, and there is nothing to parse and then also nothing to generate in the data frame. Yeah, and shall we give the answer? So the instance is class 4. This is also one of those example instances that ships with every Gurobi installation. Okay, so now with this timelines data frame, we have additional information for more involved visualizations that we can do. For instance, we can again use the glt.plot function, but this time now we pass in the timelines data frame. Here I just sliced the timelines to restrict ourselves to only this log, so only cuts 0, heuristics 0.1. So, and if you remember, this was the one log output or the one setting from our poll that had those vastly different runtimes. Seed number 2, the green run, and we see this is done in 2.7 seconds. The blue one is done in 11 seconds, and the red one is done in almost 500 seconds. If you would disable the logarithmic axis, this difference is even much more pronounced.
This is, would you mind plotting the incumbent here instead of the gap?
Mm-hmm. Sure.
Interesting. So the incumbent on the terrible performance in the beginning is actually lower than on the seed 0. Interesting.
Yeah, for at least up to 2 seconds, right? So
yeah, up to 2.
Only in the very
yeah, this is
beginning.
logarithmic. Oh,
yes.
yeah, this is yeah. No, but it's interesting. So that means that the incumbent based on the root node is better, but it's interesting. This is cool. Okay, Ed, you have your hand raised.
Yeah, I actually have it raised now about two things. So let's focus on the plots here. So can we go back to the gap?
Sure,
plot,
sure.
Or even better, show them both on the same screen if we can do that?
No, we can't do this right here in this
okay.
frame.
So go back to the incumbent now. Yeah, so it looks to me like the gap and incumbent progress are very correlated, which basically says that, and I'm not as familiar with Glass 4 as everybody else on this call is. It's sort of like the go-to model for the Gurobi staff is what I've found. But this looks to me like progress in the gap basically relates to progress in the incumbent. And that what this tells me is that the variability will go away maybe if we bump up heuristic intensity, that, we got to focus on making progress on the primal bound more so than the dual bound. It looks like based on these two charts. And sorry to interrupt. The reason I raised my hand originally was not about these plots, but that we're getting a fair number of questions along the lines of, does this tool work when instead of the Gurobi command line tool, I'm using Java, I'm using this, I'm using that. And the answer is log files don't care where they came from. Okay, you can generate a Gurobi log file from Java, from C++, from R, from any of the connectors or APIs that Gurobi allows. So this is not restricted to generating logs from a command line run. If your application can crank out a log file, you can use this tool.
And I actually want to add something. So a few people have asked about Spider. So to my knowledge, Spider also has an interactive part. And for as long as that part can render HTML Plotly, which I think it can, then this works. So basically, this is it is a bit of magic, but it's mostly just Plotly. Like it's GRB Log Tools, the parser of the log file, and then a thin layer on top of this, which basically puts that into the right, easy to use thing that you see here, but we'll go into a little bit more customizable plots a little bit later in the talk. And one other thing I wanted to say about what Ed said about the heuristics. So I think it was Jarek, or who was it? When they started at Gurobi, so everybody who starts at Gurobi in support, they kind of get glass 4. So I think he found that the no-rel heuristic, so the no relaxation heuristics, where you don't use the LP relaxation, but you go straight into submips, actually performs quite well on glass 4. So this is anecdotal. I haven't tried this myself, but it would confirm what you just said, that the key here is to make progress on the primal side using heuristics.
Mm-hmm. Okay, cool. So customizing the plots. I mean, we already talked about Spider a bit. I'm a big VS Code fan, and in VS Code, this all works fine. So I'm pretty sure Spider also works fine. But we would also like to show you that this is really just a pandas data frame. So you can actually use whatever you'd like to do if you don't like this interactivity that we just demonstrated. So here we just slice the timelines data frame to only show a single run. So we restrict ourselves to the log 912 and the 0 seed. And then we create a figure and add 2 traces. So we add the incumbent trace, the primal bound, and the best bound trace, and call it dual bound. And we also fill it to the next y, and then give it a name and objective function. So the y and x axis. And this is what we get. So you see this is already very similar. We can do the same stuff as before, right? Zooming in and investigating this plot. And this was just by using, the data frame that we already have at hand, but not using the shipped plot function that comes with GRB Log Tools. So let's examine something very similar. So again, we select this run with this hugely different runtimes, the cut 0, heuristic 0.1 log, and we only look at the fastest run and the slowest run. So seed 1 and seed 2 in this case. And then we generate a subplot. So this would look like this, where we basically do the same thing as before. We plot the incumbent and the best bound for both of those runs, but in a multi-plot basically, or in 2 subplots. And if we here change the shared x-axis value to true, you will also see how strongly different the runtimes are, because now we actually have the same x-axis scale for both plots. So we talked about the gap being the relative difference between primal and dual bound already, and I guess this is known to most of you. And now we would like to get something similar as we saw before in this plot where we had those 2 comparisons, and we would like to do this just with our shipped GLT plot function and just plot the gap for those 2 runs. So we do a slice again of our timelines data frame and just call this isIn function. So this is a pandas function that restricts our log to be either cut 0, heuristic 0.1, or the default run. So of course we get 6 different runs in this case, because we have 3 different seeds for each of those settings. And then we just call the GLT plot function again using this timelines data frame. So this basically this stripped down data frame. And this is the nice plot that we see here. So here we also set the symbol frame, or the symbol selector, to signal the seed. And the color is automatically selected by using the well, based on the log. And something very nice that we can see here is the iterations per node. So this is something that is often overlooked, I would say, because it's just something that is usually not too important to grasp how fast an instance was solved. But if you want to see how you can make it faster, this is an important aspect to check for possible bottlenecks. And here we see a very interesting result, actually. Ed, do you want to comment on this?
So that's there's certainly something strange going on with this one run, where this one seed where the iterations per node just jumps up. So, I would want to take a closer look at exactly what's happening there that caused that, because that's pretty weird to see such inconsistent results with different iterations per node on the same model just because you change the seed. Maybe, so the first thing I would do, I guess this is still glass 4, right?
Yeah, sure.
I mean, to me, that says that there probably is something odd numerically in that model that is worth understanding. It also says that a nice feature that I think we need to make more available is the ability to spit out some node LPs so you can actually run them individually to see what's going on. Because, we can go back to the node log, but the node log is not going to tell us anything more than what we see here, that there's this sudden growth. But it would be interesting to see, was there a new incumbent at that time? What else happened at that time? And to see that either by plotting some other things or looking at the text node log at the appropriate point. So, if we have to go back to looking at the node log, at least we know exactly from the plot where in the node log we should be looking.
Actually, I have a question here. Would you mind putting on the y-axis, instead of iterations per node, the depth? So where did this kink occur? I think it was around current node 1,000. Or if you go back to the integer, if you go back to the integer part.
Did this happen on the really time-consuming run?
No, this was on the seed, on the defaults. So this is defaults, and this is the kink occurs at around
this one, right?
Mm-hmm. Yeah, correct. First seed. So this is at 1,222. If we now look at the depth on this one. Okay. So we don't have any depth information there.
No.
Interesting.
Yeah, the thing is that these node LPs are very quick to solve, and we don't print enough log lines here to have a nice progress information.
That's true. Actually, we have a couple of people who have raised their hands, if you don't mind, from Srinivas. Srinivas, go ahead.
Hey, everyone. So my question is, when we use Gurobi, right? We will have some other application and we will formulate a model, pass it, right? But when we are running this, in this log, we will have other information that we may put in, right? So when we get the logs from the production systems, right, it has Gurobi information. It also has some problem specific information. How will this tool work when we have those log files?
Okay, can I answer this one, Richard?
Go ahead.
typing a response. So this Python code that Matthias has written can't know what an individual user has customized in terms of interleaving output with the Gurobi log. But this is an open source Python project. It is not as proprietary as most of what's in the Gurobi solver. So you can download the GRB Log Tools.py and, for example, modify it to skip the individual info that you create so that it will just interpret the log file info. Or if you want to incorporate the information, you could extend this and customize it to the log info that you guys create in your application, which is this mix of Gurobi information and your own information.
Yeah, thank you. Yeah.
We have one more question, Matthias, if you don't mind.
Sure.
The question is because we're actually not going to touch upon this in the talk. Does this also allow for the plotting of multi-objective optimization models?
Yes, you will also get the summary info just as before, and I think the timelines should also work fine. I'm not entirely sure. I would need to check this, but the summary is definitely fine because the multi-objective run doesn't look that much different from a normal run, right? So in the end, you still have the normal statistics. So this is definitely going to work. So getting this performance comparison, the runtime comparison, something like this is definitely possible. Yeah.
Okay, cool. Thank you. Back to you. Oh, and by the way, I think we forgot one poll question. If you go a little bit earlier, the primal and dual bound plot in the beginning, while we're at it, since we're all chatting away here.
I don't know what you're referring to right now. Shall I?
Yeah, just go a little bit back in the slides to one more. Yes, this one. Actually, we had a question here scheduled, but we were so excited about what we're seeing that we forgot. So basically, if you had to pick now, where would you see this picture, and we've already discussed this a little bit in the talk so far. Where would you focus your attention if you had to work on something? Would you put it on the primal bound, or would you put it on the dual bound, or on both? And the poll is open. I know this comes a little bit as a rush, and feel free to look at the picture again, but it's more to get a sense of how you would interpret this. Alrighty. So I know we already talked about this briefly, but majority of people, half people would focus on both, and the other half is split equally between primal and dual. Ed, I'm gonna call on you first. What would you pick?
So is this is not the really horrible run that took way longer,
No.
right? This
No,
is just a default with seed 0. Yeah. If I had to go with one, I'd go primal bound because of that long flat line stretch from 0 to 20 where nothing is happening. It seems like, and then when the primal bound starts to improve, the dual bound, which was moving but very slowly, starts to move better. But the dual bound is pretty bad too here, especially up through 25. So overall, I think both would be the best answer. It looks like there's opportunities for improvement on both bounds here. It's not like one is totally flat and the other is making a lot of progress. We see some bad stretches for both. With that, I yield back.
Yes, what do you think?
I have to fully agree with Ed on this one. This is exactly also my opinion. I mean, both bounds are moving, so it makes sense to actually look to make them move faster, both.
Fair enough. That is true. All right, Matthias, back to you. Sorry for the diversion.
That's fine. Okay, so let's jump ahead to basically one more thing, which is the Excel output. So in case you have been sitting through this presentation until now thinking, oh my God, I don't even like writing Python code. I don't know any Python. I don't want to work in Python. I'd much rather use Excel. Then we also have something for you. So you can, in fact, just run GRB Log Tools as a command line tool using the Python -m syntax. Then you would specify your Excel sheet, the output file, and then pass in your log files. And if you want to, just as before, you can also pass the timelines option or not. If you want to have just a summary or also the timelines and the node log and the root LP log. So if we run this, we see that there are 63 logs extracted to analysis XLX. If we open this file real quick, we see that this is very similar to the data frame that we saw before, just simply because this is just the very same data frame exported into Excel format. So now you can do whatever you'd like to do in your Excel environment to, I don't know, maybe also create some charts or do some data exploration and analysis. So you see those subtables here, those worksheets. Again, for the root LP, we don't have anything because the root LP information was not there in those runs. We have the node log and the summary. Okay, and with this, the presentation part is over. So as a conclusion or takeaways, go to github.com Gurobi/GRB Log Tools to find the code, find the repo, maybe post your ideas. Install it just using pip install GRB Log Tools, and then you're ready to go and draw some plots based on your already probably available log files. And we're really looking forward to getting your feedback or questions and ideas also on GitHub.
Exactly, and just to tell a little story here, that is before we wrap up here, since we have a couple of minutes left. This is not a tool that is baked into Gurobi. This is not something that ships with a product that is officially supported and what have you. The idea behind this is that a few years ago, this started off as a tool that we wrote in support because we needed to analyze log files a lot, like properly a lot. And so this was not feasible to do this by hand anymore. And so we decided to write this tool. And it grew and grew and grew and grew and grew. And finally, and this was about 6 months ago, we decided, what if we open source this? What if we know that some of our customers have asked for a tool like this? We would just make this available. And so this is what we've done here. This is meant to be a community project. This is meant to be worked on together. So everybody anybody can open an issue on GitHub. Anybody can make a pull request. We'd love to see pull requests on this where people improve. And we're not claiming at all this is perfect. You know, there's a ton of refactoring to be done. You can add unit tests. You can expand this to other use cases we don't cover or what have you. Go ahead and feel free to contribute. And this is really is a very, very open invitation to be part of this and work together on this together with us, because we're looking really forward to engaging with you guys on a very concrete level here. So, and this has really helped us tremendously. I mean, Matthias and I worked on tickets together where we had, I think was it 720 log files because we had like 3 days hourly data and then 10 random seeds and just sieving through this and finding how parameter sets did. So it was 720 per parameter set tested. We had like 10 parameter, 20 parameter sets tested. It's really, this is where this tool really shines. And so just my invitation to participate and be part of it. And we'll stick around a little bit longer if you want to. If you also have some more questions. There is actually a question here, now that I see it, is have you guys looked at any similar use cases for other programmatically generated files? Sol solution file, but .log we just covered, but like solution files or JSONs or something like this.
Well, I'm not entirely sure what this question refers to be honest.
Like,
so,
would you be able to plot different, like to put in the parse and then plot, for example, 20 different solution files?
Well, no, not with this tool. But to be honest, plotting a solution or parsing a solution file is way, way, way easier than parsing a log file, because the log file is somewhat in the middle between being intended for the human eye and containing, well, sort of like machine readable information, whereas a solution file, a sol file, is not really intended for the human eye. So, and it is very structured, way more structured than a log file.
That makes sense. There's a question for Ed here, which doesn't really deal with this, but since we're hanging around anyways, after the talk. The question is, when would we see some capabilities in Gurobi to handle complex modeling challenges like robust optimization?
Well,
no pressure.
Complex modeling challenges like robust optimization, or robust optimization specifically?
It was like robust optimization, but
right. I'm not sure how much demand there is for robust optimization. You know, it sounds really good, but at the same time, it sort of tends to give solutions that are too conservative, because you're always concerned about sort of the worst case scenario. So we haven't seen that much demand for that, but if demand grows, I think we'll respond. Gurobi has a track record in that regard, as is illustrated by the fact that we have created things like multi-objective optimization, or the notion of a solution pool or a pool of solutions. So we have a history of adding that type of functionality. But right now, I think in terms of the biggest modeling challenge we're looking at is augmenting our non-convex quadratic programming solvers. You know, that's a big modeling challenge as well. It's a fundamentally new and more difficult problem type. And I guess that's a good lead in to what is likely to be our next tech talk while we're at it.
It's true. Our next tech talk will be... sorry, go
ahead. I guess my only other comment is, what other complex challenges besides robust optimization are you thinking of?
While we're waiting for that person to answer, actually, Irv has raised his hand. So, Irv, over to you.
Yeah, this is a cool tool. I'd like to understand the following, where this could be used in a different kind of use case, which is you've got the same model and you've got 500 instances of it that are basically different data sets, and you're observing that there's different performance based upon the data that's being passed in. How would you use this, or would you create a variant of this that would try to look at the variability due to data?
Yeah, this is a very good question. We did this. I mean, we do this in support regularly, actually, and we use this tool actually to analyze these logs. So let's say you have 500 different instances of a single model, and you just run a single parameter with all those instances. So you get 500 logs. Then you could still just put the x-axis, for instance, to show maybe the model name or also the log name, and then you would be able to compare the performance and probably see which instances perform worse or are easier, which are harder. So this definitely works. So this is not restricted to the same model. They don't even have to be the same. They could be completely unrelated models if you want to.
Yeah, and actually adding to this, so the example of the story I told before of Matthias and I on the tuning ticket, this was actually a case. So we had this 3 days worth of data to 3 times 24 hours. And we actually noticed by plotting them on an hourly level like this, that we actually problems became more complicated over lunchtime. So between 10 o'clock and 2 o'clock in this particular application, this was actually something we observed. The run times became longer. It was even hitting the time limit, etc. And so we fed this information back to the customer. We said, like, guys, this is something that we observed, and we actually had a discussion around this. So this is really something that at the end of the day, it's just a pandas data frame that you can slice and dice just as you want.
Yeah, about this, I saw in the questions, there was one question about what to do if you have multiple logs in a single log file. And I just wanted to comment on this quickly. So there is an option called merged logs, and both in the Excel parser as well as in the Python function, that allows to tell the tool to actually parse every single log that is basically hiding in these log files. So because usually if you just use the same log file over and over again for multiple runs, Gurobi will not overwrite this, but rather append, so that you don't lose your previous log files or previous logs. And then you would just pass this in with merged logs equals true, and you're good to go. You just then need to check that you have some way of distinguishing those runs. But apart from that, it's all fine.
But Ed, you have raised your hand.
Yeah, I want to respond to sort of a follow-up to the previous question about where I asked about what other things besides robust optimization were people interested in, and I'm seeing a few in the chat. So let me respond to those. So the two other features being brought up are stochastic optimization and automatic Bender's decomposition. So regarding stochastic and also automated Benders, it's really the same. We go out and ask our customers and talk about this, but we don't just ask, well, do you think it would be a good idea? You know, we get lots of feedback about, well, yeah, automated Bender's decomposition would be nice, but then we sort of ask for some specific cases where it really worked well, where, you know, they used it and it worked, and we really don't get a lot of success stories. So until we see that, we hesitate to devote the large amount of time needed to add a new feature. And, you know, I'm familiar with and have used Cplex's automated Bender's decomposition and did see it be successful on you know, some cases, but we're still looking at not that many success stories. You know, on the competitive side, it's not like we've lost a lot of deals because Cplex has that and we don't. So, you know, we're very demand oriented as far as, you know, really wanting sort of concrete evidence that a feature is really going to work in practice, rather than a case where it seems like it should be good, but in fact, it won't have that many success stories for our customers. Because if we spend time on that, we're taking time away from something else that might be more important.
Okay, and I think with that we're ready to close. Thank you everyone for those who stuck around, and thanks everybody for attending. And the slides or the material in form of a Jupyter notebook will be made available after the talk.